Hi, everybody. Oh, unfortunately, I cannot see you. But so, hi, everybody. I'm Pablo Arauzo. I'm from the University of Hohenheim. I'm doing my PhD here under the Green Carbon project. And today I'm going to present one of the topics that I'm doing during my PhD, that is hydrothermal carbonization coupled with ultrasound-assisted extraction for recovery of phenolic compounds. So today is going to be based in a short introduction of this work, the objectives, the experiments, results, main results that we have, and then the overall conclusions. So what is the current situation? I think that is really clear. We still have a solid fuel necessity and is focusing mainly in two productions, energy production and for chemical industry. So we have to find some biomasses, or one biomass who can replace both applications, or at least one of them. And one of them that they choose for this study is coffee. Coffee is one of the most popular beverages in the world. And according to the International Coffee Organization, the world coffee consumption has increased from 1.14 million tons to 9.5 million tons in the last year, and in the period of 2010 to 2018. So how is expected like the population is still growing up in the next years? It's expected like also the coffee will grow up. So that means like the necessity to valorize the residues generated from instant coffee mainly, that is called like a exhaust or spent coffee grounds. We call in this study spent coffee grounds. So spent coffee grounds is the main waste from the industry after the process roasting and production of coffee. So that's the main residue that they have for the Starbucks or other cafeterias. So what's the things from these coffee grounds? The spent coffee grounds is a wet organic material with 78% water, lignocellulose structure, and we have to remark here that this lignin content is really high. Lignin content is around 22% of weight, and this lignin content allows to produce some valuable compounds like a phenol compounds. Initially, is found like a 17.92 milligrams of gallic acid equivalents per gram of initial coffee, aliphatic acids, alkaloids, and tannins. And the other remarkable things for these spent coffee grounds is like they have really low ash content, 1.30. That is good for burning purposes because the ash is deriving after the combustion. So we want to have like a low ash content. And the initial high carbon content is 50%. So this makes like a good initial feedstock after a thermochemical process or for combustion. That the high heating value is around 21.84 megajoules per kilogram of daily basis. So what is the objectives in this study? The production and physiochemical characterization of hydrocharge from spent coffee grounds for energy purposes and the extraction of phenolic compounds after hydrothermal carbonization. Why of this? Because the phenolic compounds could potentially act against cancer, cardiovascular diseases, diabetes, antimicrobial, anti-allergic, and anti-inflammatory effects. So how was the study this? I mean, we have the coffee grounds from the cafeteria from our university. Then we make hydrothermal carbonization. We use hydrothermal carbonization because hydrothermal carbonization is a wet thermochemical process that use the water content of the feedstock like an advantage to produce carbon materials. And we study 3 reaction times, 200, 230, 260, and 1 hour and 3 hours reaction times in a 250 milliliter reactor. During this time, we measure the pressure and also the temperature to figure out what is the heating rate. Then after hydrothermal carbonization, we have a slurry. And this slurry, we have 2 possibilities. The first one is like a make a separation. And we have in one side like the process water and in other the hydrocharge to make ultrasonic assisted extraction. And then after ultrasonic assisted extraction, this hydrocharge, we can make again a filtration to have hydrocharge on one side and phenolic compounds in another side. And in other way, we have directly slurry directly in ultrasonic assisted extraction. In all times in this ultrasonic assisted extraction, was used 3 different solvents: water, methanol, and water methanol with a 50% of each one. And the solid liquid ratio was 1 to 25, and the optimum was found is 40 degrees and 40 minutes for this study. Why we decide to use ultrasonic assisted extraction? Because ultrasonic assisted extraction is considered like a low cost process, and is versatile in terms of solvents that are used very fast and also reproducible at industrial scale. So now I'm going to talk about the first part, hydrothermal carbonization, until the slurry production. So this is the properties of the produced hydrocharge. In the we can see the initial ash content. When after the hydrothermal carbonization, the ash can increase slowly. That is, as I mentioned before, this is desirable for energy purposes since the ash is the remaining after the combustion. And the explanation that the high concentration increase after the hydrothermal carbonization is because there is a solid reduction after this thermochemical process. And that's why the soluble organic compounds formed during the hydrothermal carbonization try to go to the liquid phase, while most of the inorganic compounds precipitate in the solid phase. We can see here that the high heating values is increasing like almost 50% more from the 21.84 until the maximum that is found 33.17 megajoules per kilogram at 260 degrees and 3 hours reaction time. But the most significant thing is the fold ratio. The fold ratio is the division between the fixed carbon and the volatile matter. I mean, the volatile matter decreased by more or less 20.09% at 200 degrees an hour reaction time in comparison with the initial raw material. And the decrease of the volatile matter, that's why the fold ratio mainly increased, is because during the hydrothermal carbonization, there is the formation of high molecular and cross-linking. And this is why finally the fold ratio increased like 3 times more after the hydrothermal carbonization. And the hydrocharge yield decreased because with the reaction time, but it's almost independent on the time. We can see like at the same temperature and different reaction time, more or less the yield to hydrocharge is the same. I mean, we define like we use hydrocharge yield like a mass of the dry hydrocharge divided for mass of total dry feedstock. And that's most from the hydrothermal chart. And then the Van Crevelen shows the carbonization of hydrocharge, which increase with increasing severity of the reaction for its treatment in comparison with the raw material. The atomic ratios in both cases decrease. This decrease of organic oxygen-carbon ratio is mainly due to the dehydration reaction, but however, at 260 and 233 hours reaction, we can see here like the carboxylation start to take place, and it's because it's the formation of the carbon dioxide in the gas phase. So now going to the second part of this study is the phenolic compounds. So I say like we measure the phenolic compounds in 3 different parts: in the processed water without any ultrasonic assisted extraction, from the hydrocharge with the ultrasonic assisted extraction, and then from directly slurry without separation in the ultrasonic extraction with 3 different solvents. Sorry. Here. So here we can see that at the same temperatures, long reaction time that have negatively influenced of the amount of phenolic compounds because they decrease with the reaction time during the hydrothermal carbonization. This is because it's the degradation or oxidation of phenolic compounds during this process. And then the use of water is as a solvent during the ultrasonic assisted extraction for the phenolic compounds. We see that it's the lowest phenolic compounds extracted. We use water like a comparable and like a eco-friendly solvent to figure out what is the minimum that we can extract. And however, with the methanol and water methanol, we can see here like the extraction of solvents is almost like 4 times higher. The possibilities like with methanol and water methanol also we have higher extraction of phenolic compounds is because the solvent polarity affects during this ultrasonic assisted extraction, and also because the phenols and the oxidants have higher solubility in organic solvents than in water. The temperature could be also temperature generates instability or oxygen phenol compounds. So even there is in the liquid phase, some of them finally in the hydrochar also there are some decreasing. On the other hand, also it's expected like during the hydrothermal carbonization, we are making the lignification of the initial spent coffee grounds. So our idea during this process is to be able to start to decompose a little bit the lignin or go to the liquid phase, or they are more in the ultrasonic assisted extraction. So now if we figure out with the slurry, we can see that in the slurry almost the yields to the phenolic extracted compounds is almost the same in all of them. And this is, we think that is possible because the cavitation that takes place during the ultrasonic assisted extraction is affecting with the or it could be some interactions and groups and methoxy groups that they are more. So we know also that with the water, the methoxy compounds are hydrolyzed. So there is a possibility that the water content that we have in the slurry is also playing a process. It's playing a role like a hydrolyzer of methoxy groups. So the final comparison is between the slurry and in one side and hydrochar and water in other side to make sure like or have a comparison like what have more sense like directly separate before the ultrasonic extraction or put everything together like a slurry during the hydrothermal during the ultrasonic extraction and after the hydrothermal carbonization. And we can see here that if we use water like a solvent, it makes more sense to use everything together without separation before the ultrasonic assisted extraction and make the separation afterwards because the almost is double found of the slurry than in the hydrochar and water separately. So another way to understand what we are doing in the FTI during this extraction of phenol compounds, we use the FTIR, and this figure shows like the Fourier transform infrared of the hydrogen produced at 200, 230, and 260 at 3 hours reaction times after the ultrasonic assisted extraction. And difference increment with the temperature are caused by the solubility of the products. In general, we can see here that the methanol is the solvent that causes the biggest reduction of peak intensity of reduced hydrochar. It can confirm by the high extraction effects of phenol compounds in comparison with other components, other solvents. However, in the hydrochar filter at 200 degrees, the use of water methanol, 50% of mixture, produces a similar effect that only methanol solvent, which seems to cause a reduction of peaks intensity of the functional groups. This could be due to the degradation of carbohydrates that there is no completely occurred during the hydrothermal carbonization, and the not degraded lignin is accessible for the solvents by the solvents. At 230 degrees, degradation of the cellulose, we think that is completely we think, and also with the literature that we use for this study, is completely degradation of the cellulose is completed. However, the lignin again is like is degraded, but no, obviously no decomposed. And that's why the peaks of the hydrogen after hydrothermal carbonization have equal transmitted intensity. And here we can see that there is some characteristic peaks, the aliphatic peaks from carbon hydrogen between 300, 3,500 and 3,000 wavelength, and the carboxylation reaction that take place between 1,780 and 1,605 wavelength, that they are similar after hydrothermal carbon, ultrasonic assisted extraction in all the processes. The peaks of the aromatical functional groups that is usually found between 1,600 and 1,400 are also reduced after the ultrasonic assisted extraction in comparison with the initial hydrochar. You can see that it's in the red line. And these peaks are associated with the aromaticity where we use only if the methanol is used like a solvent due to the high solubility of the phenolic compounds. And the peaks of the wavelength between 1,000 and 850 are associated with the methoxy groups and other bonds. And during the hydrothermal carbonization are hydrolyzed. Plus, these peaks also support the values obtained before and evaluated by the following Catuleo method that support the extraction of phenol compounds of these groups. And the overall conclusion of this study is like a spent coffee grounds is suitable feedstock for energy production and high phenolic content. The increase of the stability of the reaction condition during the hydrothermal carbonization promotes the degradation and the carboxylation reaction. There is direct separation of total phenolic compounds from the slurry reveals higher values than separately from hydrochar and processed water. And the FTIR figures show that using methanol solvent of functional groups in the hydrochar independent that must be done, or I should continue, is check the possibility of the application of the produced hydrochars in high value phenolic compounds. And finally, I would like to say thank you to my colleagues that they are doing here, Nicola Chan, Lindu, Maciej Koczewski, and both supervisors from University of Trento and University from Hohenheim, Luca Fiori and Professor Kursa, my supervisor. So thank you very much.